in example 6, which is tied to example 5. It's still about that billiard ball. It's being dropped from a height. It's all the same setup, right? So let's go down, scan down to the very last sentence. Here's where it's different. Approximate the instantaneous velocity at t equals 1. Okay, so now this is where we're going to kind of systematically come up with that instantaneous rate of change, or at least approximate it, using a whole bunch of secant lines, some average rate of change and average velocity. Okay, so I'm going to come back over here so I have some space to write. It's this question. I'll just write it right up here so I have enough room. So we want instantaneous velocity at t equals, I think it was 1, right? And our function s of t was equal to negative 4.9 t squared plus 100. Okay, so again, at a tangent line, which is instantaneous rate of change, we don't have enough information to calculate the slope at that point because we need 2. So we're going to use secant lines, really close secant lines. And we're going to approach this in 2 directions. We're going to approach this smaller than 1 and bigger than 1. So we're basically going to build a table of values here. And I'm going to say I have S for my time. And then we're going to have secant lines, our secant slopes, at those times. The slope of the secant line. And then right here in the middle, we're going to have 1. We won't be able to calculate the slope there because we'll only have 1 point. Okay, and we're always going to use this particular point on here, right? It's always going to be the slope between 1 and one of these other points that are on the table, okay? All right, so let's back away from 1 by smaller and smaller increments. So smaller than 1 might be something like 0.999. Maybe a little bit bigger is 0.99, and maybe a little bit bigger is 0.9. So I'm going to find the slope between, say, 0.9 and 1 and write it down, 0.99 and 1 and write it down, then same thing with 0.999 and 1 and write it down, and hopefully we can see a trend of some kind. Is that zeroing in on a particular number? But to get a better idea, because sometimes like I don't know, is it stopping at a particular point? I want to look at it from the other direction as well. So I'm going to kind of make this very symmetric. So a little bit bigger than 1. So 1.001, 1.01, and 1.1. Okay. So again, every single time we calculate the slope, this is what it's going to look like. So for example, I'm going to write down what the first one is going to look like right here. We're going to calculate the slope between the points 1 and s of 1. And this is always going to be a point that we're going to use, right? Because that's the one that we're trying to calculate the instantaneous rate of change at. And then we're going to find the slope between that point and 0.9, comma, s of 0.9, right? So if we're going to use our slope formula on that, the slope, come on, that's an m, of the secant line would be equal to, let's say that I write down to s of 1 minus s of 0.9 over, in the same order, 1 minus 0.9. Okay, and then I can very easily type this into the calculator, copy, paste it, second enter or whatever, and just change my numbers for the different values that are in this table. So let's use that GeoGebra sketch that I was using before. It already has my function built into it, and now I'm going to start calculating some slopes. Okay, you're going to hear some noise here because I'm going to put this back on my keyboard. A little bit easier to do with my typing. Okay, pardon the noise. All right, let's see. I want parentheses s of 1 minus the s of 0.9. Arrow out of all of this, divided by, in the same order, 1 minus 0.9. And hit enter. Okay, notice that down here it defaults to just 1 decimal place. I can change that, I think, in the settings over here. So it is under general. There we go. Rounding 1 decimal place, I'm going to do 3. And the reason why I'm going to do 3 is because on the free response section, and even on the multiple choice section when you're using your calculator, if you're approximating on the AP exam, they expect 3 decimal places of accuracy. Either you round it to the 3rd decimal place or you truncate it, which means you just look at that digit, that 3rd place, and you write it down regardless of what comes after it. Okay, so we already have our first slope there. Now, let's see if I get a little bit closer to that tangent line. So instead of me typing that in again, I can just duplicate that. If you're doing this on your calculator, of course, you just want to hit second enter. You can pull it up and then you can arrow over and change these numbers. Okay, so I want to go up here and make this 0.99. And then down here at the bottom, same thing, 0.99. Okay, and so now we're at negative 9.751. I want to duplicate that again because I wanted to go 0.999. Duplicate. Put a 9 there. And then also put a 9 down here as well. Okay, so we got negative 9.795. So I'm going to go ahead and pull up Notability side by side with this calculator so I can write those values down in our table here. Okay, so we had, change it back to purple. The ones that we had, starting with a negative 9.31, and then negative 9.751. One more, negative 9.795. All right, so it's hard to see what it might necessarily be getting close to. But if we go over it, now we can get something that it's in between, right? I can see that it's approaching a particular number from both sides, both the smaller side, which we usually say the left side, or from the upper side, which we usually call the right side. Okay, so let me come back to GeoGebra, and now we're doing the ones that are bigger. So I'll duplicate it again. Go up here and then change these second numbers to 1.001, same thing down here at the bottom. Okay, we have negative 9.805. Duplicate that. Let's step away by a little bit more, get rid of one of these zeros in each of these. Make that 1.01. And we have a slope of about negative 9.849, and then one more. Just make it 1.1. And this one shot all the way up to negative 10.29. Okay, so I'm going to do the same thing that I did before. Noise, noise, noise as I take this off of the keyboard. Okay, so our first one was negative 9.805. And then negative 9.849. And then finally, negative 10.29. Okay, full screen that. Shrink that down to a reasonable size. So you, excuse me, you can see that we are approaching a particular number, at least it looks like it, from either side. From either side of 1. So the trend seems to be negative 9 point something, and it's right in between negative 9.795 and negative 9.805. So I'm going to say that that is approximately negative 9.8. And again, this is approximation. This is the best we can hope for at this particular moment. What are the units here? Well, the units are going to be exactly the same that they were on the average rate of change, because we did the same exact slope. We're just doing smaller and smaller increments here. Like this change in time is getting smaller and smaller. It's approaching 0 here, meters per second. And one last time, let's model that process of actually interpreting our answer in the context of this problem. So this is an instantaneous rate of change. We want to say the instant at which this is happening. So we're going to say at t equals 1 second, the ball's instantaneous velocity is approximately, because we approximated it with an average, negative 9.8 meters per second. And there you have it, ladies and gentlemen. There is our first calculus lesson under our belts. That concluded the second objective, using an average rate of change in order to approximate an instantaneous rate of change. Prior to that, on objective 1, we were talking about local linearity to approximate. It says approximate a slope function. We actually used it to approximate the slope of a function at a particular point on that graph by zooming in until it looks sort of like a line. So if you look at your assignment, we have a handful of questions from our book, and then I also put together a supplement which you should be able to find online on Canvas.